Alright, this video is a correction to your notes from 4.4, the second example. The definite integral from 0 to 2 of the absolute value of 2x minus 1 dx. So for this one, let's think about what the graph of the absolute value function looks like. Well, when it's positive, the graph of 2x minus 1 is my graph, which has a y-intercept of negative 1 and a slope of 2, 1, 2 over 1, and 1, 2 over 1. So it looks something like that. On the left-hand side, it's negative 2x plus 1. So it looks something like that. I switch which line I use at a half. So I need to break this into two intervals, 0 to a half and a half to 2. So on the side from 0 to a half, I'm using the negative function. So that is actually negative 2x plus 1. And on the right-hand side, I'm taking the area of just regular 2x minus 1 dx. So we have to split that apart into two pieces because of the absolute value and the v shape. So to take our antiderivative, we get the antiderivative of negative 2x is just negative x. The antiderivative of plus 1 is just, negative x squared. The antiderivative of plus 1 is just x from 0 to a half. Put that in parentheses. Plus, the antiderivative of 2x is just x squared. The antiderivative of minus 1 is minus x. And we'll do that from 1/2 to 2. Now remember, our fundamental theorem of calculus tells me that I can plug in the 1/2. So I take negative 1/2 squared is 1/4 plus 1/2 minus, if I plug in 0, I get 0. There's that first piece. Plus, we're going to plug in 2. I get 2 squared, which is 4, minus 2. Minus, plug in a half, I get 1/4 minus 1/2. And now we're going to simplify this whole thing. Negative a fourth plus a half is 1/4 minus 0, boom. Plus, we get a 2 minus, that gives me negative a fourth, so plus 1/4. So I have 1/4 plus 2 plus 1/4, which is 2 1/2. And you know how I feel about mixed numbers. We'll call that 2.5 or 5 over 2 as our area.